I should probably mention, I hope this stuff hasn't completely scared you off of being an actuary. It is stuff that you can definitely get better at with time, okay? You put the time, the effort in, you work at it, you can get better. It can definitely seem less daunting over time. I should also probably mention that this financial math class next summer, even though you need Calc 2, you do not need any probability and knowledge, okay? What you'll need from Calc 2 is some other stuff we've done recently with geometric series. You do present and future values, but no probability. So we're not talking about random variables at all in the financial math one, okay? That's for a more advanced thing. You're just getting a glimmer of some things here, and it does get easier with enough effort and work put into it. All right, for lecture C, two things. We're going to do a few normal curve problems. We did talk about normal curves a little bit about 2 or 3 weeks ago, I think. Introduce the idea of a sequence in chapter 9. We've already talked about geometric series. Sequences and series are related to each other. All right, I want to assign a few normal curve problems for the next assignment. And you'll definitely be able to use Mathematica or even your calculator to do the calculations for you. But once again, you need to communicate to the grader what calculations are you doing, what intervals are you doing, what equations are you solving. Use your technology to get the answers. A normal curve is a special kind of bell-shaped curve. I did mention that before. It's about like that. Not just any old curve that looks like that, though, is a normal curve. It's got a special kind of formula. It's PDF, little f of x, has a special form. It's 1 divided by a number called sigma. It's a lowercase sigma, not a capital sigma. They look pretty different than each other. 1 over sigma times the square root of 2 pi times e raised to the negative x minus some other number called mu squared over 2 times sigma squared. Kind of a complicated formula. It is in your book, by the way, if you've been diligent about doing your reading. It's at the end of section 8.8. I'm looking at page 478 to see this formula in a box. What are mu and sigma? Mu is called the mean of the normal curve, and it's where you think it should be, at the center of mass. Because of symmetry, that's going to be right below the peak. That's going to be the value of mu. By the way, this Greek letter mu, I think it's great that it's called mu, because it kind of looks like an M and it kind of looks like a U. It's like a mixture of an M and a U, and we call it a mu. And that's not a joke, okay? Well, it's sort of a joke, but it's great that it's called mu. Halfway between an M and a U. What about the other number, the lowercase sigma? That's called the standard deviation of the normal curve. And if you mark off the inflection points of this graph on either side of that vertical line of symmetry, that distance right there is what sigma is. And this is, you try to make the drawing so that they're the same, but it looks like in my drawing this one looks a bit bigger than that one, but it's because it's not a perfect drawing. This is a normal curve with mean mu and standard deviation sigma. Is it really a PDF? Is the area under it equal 1? Yes, it does. But as an integral, to find the area, x can be any number, so you have to go from minus infinity to infinity when you do the integral. It's like a doubly improper integral. Which means, in reality, if you define it in terms of limits, there are kind of like 2 limits going on. One is the upper limit goes to plus infinity, and one is the lower limit goes to minus infinity, and you have to, both of those limits have to exist. Put the formula in here. 1 over sigma times square root of 2 pi times e to the negative x minus mu squared over 2 sigma squared. I think Mathematica will go ahead and tell us the answer is 1 here, even though I haven't specified mu and sigma. I think, I hope. Oh boy, it's working. Maybe it's not sure if mu and sigma are real numbers. That could be some trouble it's having. Yeah, it's not sure if they're real numbers. Okay, we got to plug in particular numbers for mu and sigma. I can plug in any number for mu, positive or negative. I do need to pick something positive for sigma. Standard deviations can't be 0 or negative. Well, they can be 0 for data, but not for a distribution. So I think I'll plug in like 5 for sigma. Try to put a times there. And 3 for mu. Should get 1. Anything for mu and something positive for sigma, you'll always get 1. I'll try something else. Okay, I'll plug in 7 for sigma. And negative 17 for mu, I will get 1. The area is always 1. Okay? It is a PDF no matter what mu and sigma are. You're going to have problems where you have to find probabilities based on a normal model. For example, you're going to do number 12 on page 479. It says, the speed of cars on a road are approximately normally distributed with a mean of 58 kilometers per hour and a standard deviation of 4 kilometers per hour. So mu is 58 and sigma is 4. You know what I said there? The cars on the road, they have different speeds. On average, their speed is 58 kilometers per hour and their standard deviation is 4. That's based on doing experiments to test that. If that was the case, if mu is 58 and sigma is 4, to find, for example, the probability that a randomly chosen car is going between 55 and 60 kilometers per hour, you would integrate from 55 to 60. This function, with the appropriate value of mu and the appropriate value of sigma, mu was 58, sigma was 4. This would be the probability that a randomly chosen car is between 55 and 60 kilometers per hour. Before I have Mathematica calculate this, I want to guess the answer. And this is based on some knowledge that I have of statistics since I've taught stats before. So the center of this distribution is 58. The standard deviation is 4. That means this point right there is 54, and this point right there is 62. I'm trying to find the probability that a randomly chosen car is between 55 and, what did I say, 60? Yep, 60. It's going to be the area under the curve between 55 and 60, because it's a PDF. Now, I happen to know, because I've taught stats so much, that the area under any normal curve between mu minus sigma and mu plus sigma for that normal curve is close to 68%, 0.68. So the answer here is going to be less than 0.68, because that would be the area between 54 and 62. How much less than 0.68? That's a little hard to say. I'm going to guess maybe 0.4 or 0.5 something to give myself a big range. This may give the exact answer in a strange way here. Yep, it does. Okay, approximate that. I'm guessing between 0.4 and 0.6. Yay, okay. If I had done 54 to 62, between mu minus sigma and mu plus sigma, and numerically approximate this, it's going to round to 0.68. It's bigger than 0.68. 0.68269. That's just from my experience teaching statistics. Okay, that I know. It's a 68% chance of being within one standard deviation of mean for normally distributed data. What's this ERF thing? That's a special function. It's called the error function. Have we mentioned the ERF before in here? Yeah, we have. called error function because it's related to errors in experiments. Oftentimes, errors in experiments, when it's not biased, random errors are normally distributed. Actually, it's funny, it's something I mentioned in my real analysis class this very day, this morning. That was the case as well. What's the CDF for the normal distribution? It actually is it's not a function you're used to. It involves ERF. As an integral, let's go ahead and use the same standard deviation and mean as the problem with the cars here. As an integral, you could write it like that. Integral from not 0, but minus infinity up to x. This is going to be an antiderivative of the given PDF. It will be the CDF. Since any value is possible for x in the formula, that's why you have to go to minus infinity for the lower limit of integration. Now in reality, right, the cars can't go negative miles per hour or kilometers per hour. So for the cars, it's only an approximation. You're not going to go negative. We're not talking about velocity, we're talking about speed. But anyway, this should be the CDF. Will it come out as an actual formula involving ERF? Perhaps. Yep, it does. So that evidently is the CDF for this PDF. And we could plot it. Let's plot both functions here. Do the magic of copy and paste. So here's your normal distribution right here. Copy and paste the CDF involving ERF right there. Graph this between, it's going to be most relevant to graph it close to 58. I'd like maybe 30 to 90. Let's make the PDF red and the CDF blue. Right, there they are. CDF, that's your normal curve. This is the PDF for it. Notice it does approach 1 as x goes to infinity. It approaches 0 as x goes to minus infinity. The vast majority of your area is between 48 and 70 or so. Negligible area otherwise. And so it's a good enough model even though you can't go negative kilometers per hour. Okay. So in your normal curve problems that you'll get for the next assignment, use your technology, use Mathematica, or use your calculator. You can plug the formula into your calculator as well for specific mu and specific sigma. Have your calculator do the integral too. And maybe everybody should practice that just in case I put it on the next exam where you have to use your calculator. All right, for the remaining time, about 10 minutes here, we're going to introduce the idea of a sequence, which I forgot to put in here. Intro to sequences. Okay, so we are going to start section 9.1 here. Again, we've done 9.2 already a little bit. We're talking about finite geometric series. Geometric series in general, including infinite geometric series, is the subject of section 9.2. What is a sequence? Well, at the most basic level, a sequence is something that you've learned about even ever since first grade. Like a list of numbers with a pattern. 2, 5, 8, 11, get it right here, 14, 17, 20, etc. That's a sequence. What's the pattern? My kids, when they were in first or second grade, they'd say this, the pattern is plus 3. Right? Add 3 each time, starting at 2. So that would be one example of a sequence. Another example would be, this was one of my daughter's favorite ones. This one here. 2, 4, 8, 16, 32, 64, 128. Keep doubling each time. The pattern is times 2. Multiply by 2 to get the next number. This is like terms in a geometric series. Common ratio being 2. And she used to enjoy seeing how far she could get in her head. How far can I go in my head? Not super far. I'm not real great at arithmetic, though I'm okay at this one for a ways. 192, 16,300, and now I start to slow down. 32,000, I think I'll stop after this one. 32,768, I think. Look good to people? So we keep doubling each time to get to the next term of the sequence. So again, at the most basic level, a sequence is just a list of numbers. And actually, in general, you think of it as an infinite list of numbers. These patterns can go on forever. Though you might feel like stopping at some point, and you might wonder, what is, for example, the seventh term of a sequence? Well, this one here is the first, second, third, fourth, fifth, sixth, seventh. That's the seventh term right there. Okay? Getting a little fancier. Maybe I should do one more example. Here's another sequence. 1, -3, +9, -27, +81, -243. That's a sequence too. You can have negative numbers. Here, the common ratio for the corresponding geometric series would be -3. Keep multiplying by -3 as the rule to get to the next number. To be a little bit more fancy in describing what a sequence is, sequences can have formulas, algebraic formulas. For example, could we come up with a formula for this one? I'll call it S sub n. Sometimes it's called A sub n. Maybe, I forgot what it was. Use S or A. It kind of matters to some degree for the other topic. I see they use S's, actually. Okay. Sometimes people use A sub n as the other common letter to use. S sub n represents the nth term of the sequence. Could I, for example, come up with a formula for Sn for this sequence? The first term is 2, the second term is 5. Yeah, I think so. A little bit of guessing seems to imply, wait a minute, no, that's not quite right. But that should work. When n is 1, that's 0, I get 2. When n is 2, I get 3 times 1 plus 2 is 5. When n is 3, I get 3 times 2 plus 2 is 8. This matches that sequence. Of course, you can expand this out and simplify to 3n minus 1. That's what that would simplify to. Yeah. Okay, so I can come up with a formula for that. In other words, it's really a function. It's not usual function notation. I'm not writing S of n, though I could, if I wanted to. It's more traditional to put the n in a subscript here. And it is also important to emphasize here that typically n varies over the positive integers. 1, 2, 3, 4, 5, 6, etc. It doesn't take on fractional values or irrational values between integers. Sometimes we start n at 0. And theoretically, there's nothing stopping you from starting n at 7 or at -15 and letting n increase by 1 each time. There's nothing stopping you from doing that. It's just typically you start n at 1. Sometimes we also start n at 0. Most of them. What about the next one? Can I come up with a formula for that one? I think so. Oops, Sn. Let's see. Powers of 2. If I put 2 to the n, I think that works. 2 to the n, that's something that simple. When n is 1, that's 2. When n is 2, that's 4. When n is 3, it's 8. That's the formula for the second thing. If I had started somewhere besides 2, like 4 or 8 or 16, it'd be a little bit more complicated. I have to make adjustments. For example, if the sequence had started at 8, and that corresponded to n equals 1, I could do it this way. 2 to the n plus 2 would be the formula for this one. So that when n is 1, I have an output of 8. What about this one? Well, Common ratio is -3. So I'm probably going to want like a -3 to the n in here. But if I want it to equal +1 when n is 1, I think I better do this. Then when n is 1, this is -3 to the 0 power, which is 1. When n is 2, this is -3 to the first power, which is -3. When n is 3, it's -3 to the second power, which is +9. There's a formula for that. These are called direct formulas. Sometimes sequences are defined by what you might call indirect formulas. More officially, typically called recursive formulas. You might say S1 is some number, call it 3, just to pick something. And you might say S sub n plus 1 depends on S sub n, the previous value. Maybe it's 2 times the previous value minus 1. If that's the case, I can find the terms of the sequence like this. S2 would be 2 times S1 minus 1, which is 2 times 3 minus 1, which is 5. S3 would be 2 times S2 minus 1, which is 2 times 5 minus 1, which is 9. S4 would be 2 times S3 minus 1, which is 2 times 9 minus 1, which is 17. Do one more. S5 would be 2 times S4 minus 1. 2 times 17 minus 1 is 33, etc. I could keep going forever, in theory. Let me end class today by just mentioning that you can visualize sequences in 2 typical ways. One is you can make an actual graph analogous to a graph of an ordinary function. Well, let's do this one, for example. Right here. Make n the horizontal axis, and make the values of the function, whatever you want to call them, maybe I should label it Sn, the vertical axis. When n is 1, the value is 2, make a dot there. When n is 2, the value of the sequence is 5, make a dot right there. When n is 3, the value of the sequence is 8. Make a dot right about there, etc. Do not connect the dots, typically at least. Sometimes we connect them just because we feel like it. But technically speaking, we're only plugging in positive integer values for n. So technically speaking, we should not connect the dots. So that's one way of visualizing a sequence. Another way of visualizing a sequence is just on a number line to imagine the points sort of popping into existence in succession. Say 0 is right here. Let's go ahead and make a scale. 0, 1, 2, 3, 4, 5, 6, 7, 8, etc. The numbers 2, 5, 8, 11, etc. You just imagine a movie in your mind, and we could actually animate it with Mathematica. First 2 pops into the existence, then 5, then 8, then 11, then 14, etc. So you could imagine it as an animation, the points popping into existence as time goes by. You also can just draw them all, or at least some subset of them, and maybe draw arrows indicating how the values keep changing. Although arrows are not typically drawn. If you look in the book, you won't typically see arrows, I don't think. Sometimes they're labeled with like an S1 and an S2 and an S3, etc. But some people put arrows to indicate what's happening to the numbers from one spot to the next. So those are the most 2 typical ways of graphing sequences. We've got our most typical ways of defining them, direct formulas and indirect formulas. Recursive formulas is the official name. And graphing them as ordinary graphs where you do not connect the dots and as points on a number line. Okay? So you'll get some problems like this from section 9.1 in the next assignment as well.